Before starting any analysis, it's important to understand the goals of the analysis. Here are some recommendations for analyses which may include least squares regression. First, work to understand the fundamental principles associated with the relationship between the dependent and independent variables. Second, based on the goals and the analysis of the study, take and utilize as much high-quality data as is feasible and reasonable across the entire range of interest. Third, based on the best understanding of the fundamental principles and the desired purpose of the least squares regression, use the most appropriate mathematical models to describe the relationship between the dependent and independent variables. Although for simplicity in this video, only bivariate polynomial equations were used in the least squares regressions, this does not by any means imply that they are the most appropriate equation forms for your analysis of interest. To analyze the goodness of the least squares regression, use the most appropriate of multiple quantifiable statistical metrics, including but not limited to the R-squared value, the adjusted R-squared value, and the standard error of the estimate, all of which will be shown in this video. One common method for estimating the relationship between a dependent response variable and independent variables is called a least squares regression. In this section of the presentation, we'll be talking about a linear regression model, where this is the equation for linear regression, relating the independent variable x to the dependent variable y. Consider the case where we have four pairs of bivariate relationships between x and y, shown as the black diamonds. And the relationship model between the x and the y parameters is this linear relationship shown by this red curve. Now, the residual or the error is the vertical distance between the estimated value using the model form of the dependent variable, here y hat 2, to the y value, that same point of the measured value. And so we can see we have four residuals. A least squares methodology looks at each of these residuals and squares it and sums them up and creates a function which is that sum. Note that each term is a positive term, since whether this value is positive or negative, it's being squared, it turns out to be positive. Substituting in for each of the response-dependent variables, for example, y hat 1, with the model form of the relationship between the independent and the dependent variables, we now have this form of this function f. Squaring this residual for each of the four data points, we have this representation of the function f. Squared function f in terms of the two parameters of the model, m and b, the slope and the intercept, can be written as here. So you can see there's terms which involve m, which involve b, and here one with the product of m and b. The sum of squares function f for the linear regression model has terms, which are functions of the independent variable and the dependent variable. Some terms are the sum of all the independent variables square, product of the independent and dependent variable, the dependent variable and dependent variable squared. If one has four bivariate pairs with these values, xy values, these sums can be completed, and the resulting sum of squares function is shown as follows. One may recognize the geometric form of this sum of least squares function as an elliptic paraboloid. It's linear with respect to the sum of squares function. It is squared with respect to the parameters m and the parameters b. This function, as you recall, was a sum of squares, and since each individual term is a positive, the total result is always going to be a positive. Since the coefficient of the m squared term is x squared, which will always be positive, and the coefficient of the b squared term is n, which is the number of bivariate pairs, is also always positive, then this elliptic paraboloid will always open upward. In this example case, with the four bivariate pair values as shown, the sum of squares term results in a elliptic paraboloid which has a view from above, kind of like this, where you can see there's the b axis and the positive m axis direction, and the upward direction is the function. If one looks at the bf plane from the positive m axis, you see this shape. If one looks at the mf plane from the positive b direction, you show this view, and you can see there's the vertex of this elliptic paraboloid. The intersection of any plane which is parallel to the BM plane, which is above the vertex, the intersection of that plane and this surface will form an ellipse. The intersection of any plane where m is a constant which intersects this surface will form a parabola. The intersection of any plane where b is a constant and the surface of the function f will also form a parabola. One of the helpful features of the sum of squares function f is that it's the sum of squares of the residual. We know each component residual squared is going to be non-negative, and therefore the sum of squares function is also non-negative. And this would not be true, for example, if it was just simple sum of residuals, which can be both positive and negative, or the sum of residuals cubed, which can again be both positive and negative. In order to find where the sum of squares function is a minimum with respect to each of the parameter coefficients in our model equation form, we take the partial derivative of the sum of squares function with respect to each one of the model equation coefficients. For example, here, take the partial derivative with respect to b, the intercept, and we take the partial derivative of the sum of squares function with respect to the coefficient m. This gives us as many equations as there are terms in the model equation form. These two equations may be written as this, or in matrix form as this. Using the property of matrices, we can solve directly now for the two coefficients, which in closed form can be shown as here. These are the values of the y-intercept b and the slope m, which minimizes the function f. For the model equation form with a slope and an intercept and these 4 data points, this is the resulting equation which minimizes the sum of the squares of all the residuals. The coefficient of determination, designated as r squared, is the proportion of the variation of the dependent variables predicted by the independent variables given the input data in the model equation form, which relates the dependent and independent variables. It provides a quantifiable estimate of how well the observed outcomes of the input data points are replicated by the model based on the proportion of the total variation explained by the model. The most general definition of the coefficient of determination is that r squared is 1 minus the sum of squares residual over the sum of squares total, where the sum of the squares of the residuals, or errors, is what was minimized in our least squares methodology, which is the sum of the squares of the difference between the estimated dependent variable and the input dependent variable at each of the input data points. The sum of squares total is the sum of squares of the vertical distance between the input data point dependent variables and a constant for the dependent variable. In the sum of squares total, a constant is used for the dependent variable, since if the dependent variable is truly independent of the independent variable, then regardless of the value of the independent variable, the dependent variable would be a constant. But what should this constant of the dependent variable be? Well, if the model equation form has an intercept term which is solved for, then the dependent variable best estimate is the average of the dependent variables for all the input data sets. Therefore, if the model equation form has an intercept term, the average of the dependent variable values is what is used in the total sum of squares equation. In our example case with its 4 data bivariate pairs, which minimizes the sum of the squares of the 4 residual vertical distances, ended up with these 2 coefficients for the model form from which one can estimate the dependent variable from the independent variable. The sum of the squares residuals is the square of the sum of the difference of the 4 data points relative to the model estimates for each data. For our example case, numerically, this turned out to be this. The sum of squares total for example case is the sum of the square of the difference between the singular constant value, which in this case, since we had an intercept term in the model, is the average of the input values minus the response value of each one of the points. Numerically, for our example, that turned out to be this. Putting these numbers then into our general form for the coefficient determination, we get minus sum of squares residual or the sum of squares total. This r squared value suggests that based on the model data set and the model values and the assumed model equation form, that the variation of the dependent variable y, which is predicted from the independent variable x, is approximately 88.9%. If the sum of the squares of residual equals 0, therefore the estimated data points and the measured data points are exactly on top of each other, then this term would be 0 and the r squared would be 1. The opposite end of the spectrum is if the model did no better than just a horizontal constant line, in which case the sum of squares residual would equal the sum of squares total. This ratio would be 1 and the r squared value would be 0. If one runs a least squares analysis and gets a coefficient of determination r squared, which is quite high, close to 1, does that equate in meaning to the dependent variable being well determined from the independent variable? Well, not always. The r squared value can often be quite misleading and can be often unwarrantedly high. And there's multiple reasons for that. One is that the data points used to determine the model and its coefficients is not truly representative of the process. Therefore, it's always good to have as much high quality data from a reliable and accurate source as possible. Another is that the model equation form has more coefficients that are determined, or degrees of freedom, than are realistic in the problem, and therefore the model doesn't truly represent this relationship. It's often helpful to use an adjusted R-squared value to account for some of the potential deficiencies in the R-squared value. The adjusted R-squared value statistically accounts for the number of predictor values in the model, as well as the form of the model. Adding more predictor terms to the model almost always increases the R-squared value. The adjusted R-squared value looks at the model equation form and the number of predictor terms and compares the results to how it would be expected just by statistical random chance. While the R-squared value ranges from 0 to 1, the adjusted R-squared value will never be greater than the R-squared value and is a maximum of 1. At the same time, the R-squared is 1. However, unlike the R-squared, the adjusted R-squared value can be negative. The general form of the equation used to calculate the adjusted R-squared value is shown here. You can see it's very similar to the equation used to calculate the R-squared value, but it includes this additional ratio. And this additional ratio acts to adjust to account for these additional terms and the random chance, where n is the number of data point observations used to fit the model, and p is the number of independent parameter coefficients used in the model. And beta intercept is a term which is 1 if the model includes the intercept term, and 0 if the model does not include the intercept term. For any data set in model form for which a least squares analysis can be done, this ratio is at a minimum 1. However, for most cases, it's greater than 1, therefore making the adjusted R-squared value less than or equal to the R-squared value. In the example case, there were 4 input data sets, therefore n is 4. The model equation form had 2 independent parameter coefficients that were solved for, therefore p is 2, and the model had an intercept coefficient term which was solved for, and therefore beta intercept was 1. The residual sum of squares was as before, and the total sum of squares was as before. For this data set and the form of the equation used, this adjusted R-squared value suggests that approximately 84.8% of the variation of the dependent variable y is predictable from the independent variable x using this equation form. Consider another least square regression model, this time a linear model in which the dependent variable is related to the independent variable by a simple linear slope coefficient, and there is no intercept coefficient. As before, the least squares function f is the sum of the squares of the difference between the estimated dependent variable and the input dependent variable value for each one of the input terms. And since each one of these terms is squared, f is a positive number. Substituting in for the estimated dependent variable with the equation form, we end up with f being this. With algebraic rearrangement, we get this for f, and the function f as a function of m can be written as this. For example case with this 4 data bivariate pairs, putting the values for the dependent and independent variables, this equation results in this, or our sum of squares function f as a function of m. One can recognize that this sum of squares function f with the associated model equation form is a second-order equation of the function of m and represents a parabolic relationship. And we see that the coefficient of the second-order m squared term is a sum of the independent variable squared, which is always positive. We know the vertex will be minimum and the parabola always opens upward. The figure below for our example input conditions shows the shape of the geometric form of this parabola, with the sum of squares function being a function of the slope. We're solving this equation at its vertex, we get these values. For this regression model equation form, the sum of squares function f is this. We know that the sum of squares function is always a positive. To find the value of m at which this sum of squares function is a minimum, we take the partial derivative of the function with respect to m, which gives you this, and we set it equal to 0. Solving for m, we get this, which is the sum of the product of the dependent and independent variable over the sum of the independent variable squared. This is the slope value m, which minimizes the sum of squares function f, which is the cumulative sum of squares of the vertical distances. For our example case with its 4 bivariate pairs of independent and dependent variables, the least square solution gives this value for m, which minimizes the sum of the squares of the residuals, and with this case having no intercept term and therefore an intercept of 0, 0. The general form of the coefficient of determination equation is the same as it was before, despite the change in the model equation form. The sum of the squares of the residual is the same as before. It's the sum of the squares, the residual, which is the difference between the estimated value of the dependent variable and the dependent variable input values. But in this case, the estimated value of the dependent variables differ because it has a different equation form. The sum of the squares total is once again has the same general formula, whereas the sum of the squares of the difference between a constant value of the dependent variable, assuming independence between the independent variable, the dependent variable, and the actual dependent variables. However, in this case, where the model equation does not have a defined intercept term, which essentially means the intercept is 0, a valid point would be when the independent term is 0, the dependent term would also be 0. So therefore 0, 0 would be a point using this model equation form. And truly, if the dependent variable is independent of the independent variable, and we know one point in that relationship, which is 0, 0, this model equation form tells us, therefore, if truly there is no correlation and they are independent, then the dependent variable will be that value for all values of the independent variable. So in this case, our constant value is 0, which is this intercept term. And if the dependent constant value is 0, then the sum of squares total is, for this case, where there is no defined model intercept term, the sum of squares total is the sum of the squares of the dependent variable input values squared. For the 4 input data bivariate pair values, this model equation form, the sum of the squares of the residuals turns out to be approximately 0.84, which is more than double the case when the model equation form had a slope and an intercept term, in which case the sum of the squares residual was approximately 0.378. Since the model equation form had no intercept term which is solved for, constant term is the constant term in the equation, which in this case is 0. So the sum of squares total is the sum of the squares of the difference between this constant term and the dependent values, as shown here. And if we sum of the values for these 4 data bivariate pairs, the sum of squares total turns out to be 16.7. And as expected, this is significantly larger than the sum of squares total for the previous case, where the model equation form had a slope and intercept term, and therefore the constant was the average of the dependent variables, and that sum of squares total was 3.74. The general form of the adjusted R-squared equation is as before. For the example case with the model equation form being this, the number of data points is 4, so n is 4. The number of parametric coefficients solved for in the model form is 1, so therefore p is 1. And the equation model form has no intercept term which is solved for, and therefore beta intercept is 0. Putting in the sum of squares residual and the sum of squares total into the equation for this example yields an adjusted R-squared of 0.933, while the R-squared was 0.95 for this example. This suggests that based on the model equation form and the data, approximately 93.3% of the dependent variable values are predictable from the independent variable. Even when the dependent and independent terms are actually totally independent of each other, the average expected coefficient of determination is not 0. It will be greater than 0 and depends on things such as the number of independent terms in the model, or the order of the polynomial equation of the model, n, the number of observational data points, and whether or not the model equation form includes an intercept parameter coefficient. For cases where the dependent variable y is totally independent of x, such as when the dependent variable y's are totally randomly generated independently of x. For cases where 3 conditions are all true, first, that the dependent variable y is totally independent of x. The second condition, where the actual average value of the dependent variable y is consistent with a model equation form, such as these equation forms when there is no intercept term, that the average value of these randomly generated dependent terms is 0, and therefore consistent with the model equation forms. The third condition being that although the polynomial may or may not include an intercept term, the rest of the polynomial is complete. If these 3 conditions are held true, then the average coefficient of determination, or the average R-squared value, may be calculated using this following equation, where the numerator is the order of the polynomial, which is the highest exponent of the independent term. And the denominator is n, the number of observational data points, minus the b-intercept term, which is either 1 when the model includes the intercept term, or 0 when the model doesn't include an intercept term. For these conditions, when all the dependent variable values are randomly generated independent of the independent variable, the average coefficient of determination that one would get as a function of the number of input observations used to fit the model is shown in this graph below. When the model equation form is first order, this numerator is 1. If the model equation form has no intercept term, the b-intercept is 0. This equation simplifies to an average R-squared value of 1 over n. Therefore, if n is 1, the average R-squared value will always be 1. And for example, if n equals 4, the average R-squared value would be 1 over 4, or 0.25. Even though all 4 of these dependent variable values of y would be randomly generated. As shown in orange, if the model equation form is first order and has an intercept term, then the numerator is 1 and beta-intercept is also 1. And the average r-squared value for that case would be 1 over the quantity n minus 1. Therefore, if 2 data points are used, we know that a line can always be perfectly fit, despite the fact that the dependent variable values are randomly generated. So the average r-squared value will always be 1 at that case. The number of input observations used, n is 4. In this case, 1 over the quantity 4 minus 1 is 1/3. Therefore, even though all 4 of the dependent variable values are randomly generated, on average, the average coefficient determination r-squared would be 1/3. As shown in green, if the model equation form is a second order one but does not include an intercept term, then in this equation the numerator is 2 and beta-intercept in the denominator is 0. Which makes the average r-squared value be 2 over n. So for the case where n equals 4, the average r-squared value one would get would be 2 over 4 or 1/2. For the case where all 4 values of y are randomly generated independent of x. As shown in blue, if the model equation form is a complete second order model, including an intercept term, the numerator is 2 and beta-intercept is 1. And therefore, the average r-squared value, where x and y are totally independent, would be 2 over the quantity n minus 1. And for the case where n equals 4, this results in 2/3 as my average r-squared value, despite the fact that x and y are totally randomly generated. Despite the fact that all 4 values of y are randomly generated. And for the last model equation form shown in the curve, where the polynomial order is 3, but the model does not include an intercept term, the numerator is 3 and beta-intercept 0. And therefore the average coefficient of determinant will be 3 over n. And when n is 4, the average r-squared value will be 3/4 or 0.75, despite the fact that the dependent variable values are all randomly generated. Even for the cases where y is totally independent of x, the average r-squared value, or the expected r-squared value one would get from a singular case, increases when the number of model parametric term increases. For example, when the polynomial order increases. And both the average coefficient determination and expected coefficient determination increase as the number of data points decrease. In conclusion, you can see that the average r-squared value has a positive bias, and that positive bias increases as you increase the number of model terms, and also increases as you decrease the number of input data observations. And this average r-squared bias decreases as you add more observations. This average bias decreases as you make your model have less terms. In the previous slide, we talked about the average r-squared value one could expect when the dependent variable y is generated as a Gaussian or normal or bell-shaped random white noise function, which is actually independent of x. In this slide, we'll go into more details on a particular case. Similar to cases where, for example, you flip a coin multiple times, for example, 6 times, and you happen to get 6 heads. Even though the coin can be random, patterns sometimes appear to emerge even out of the randomness, as it's just a matter of statistical chance. The same is true for an individual case of an r-squared value estimated from a single data set. Even when y is truly independent of x, a particular case may have an r-squared value as low as 0 or as high as 1. The figures below show an example representative case when the model form is a complete quadratic second-order polynomial, and there are 5 observation values used to fit the model, and the dependent values are all generated as white noise. The graph on the lower left shows the probability density function for r-squared as a function of r-squared for this model form, and n equals 5. One can see for this particular case, one has equal likelihood of getting an r-squared value anywhere between 0 and 1 for any particular data set. The graph on the lower right shows the cumulative distribution function for r-squared as a function of r-squared. For this case, where the cumulative distribution function is the integrated quantity from -infinity up to any value. And for this particular case, since the probability density function is a constant, the cumulative distribution function is a straight line, where the cumulative distribution function has a value of 0 at the minimum real value of the coefficient of determination, and 100% of the values will occur at a value less than this. And as one may recall from the previous slide, for this model form and these number of observations, even when y is randomly generated, the average value of r-squared will be a half. As a result of random probabilistic chance, even when the dependent variable is totally independent of the independent variable, the r-squared value can vary with every data set. The figures below show the cumulative distribution function for r-squared for different cases. Both figures are attained when the dependent variable values are all randomly generated. The figure on the lower right was when the number of observations was 5, and the blue curve on this graph was discussed in the previous slide. The figure on the lower left is when the number of observations was 4. In these graphs, the probability of getting a higher R-squared value from any data set when x and y are actually independent increases as the number of data points decreases, and also increases as the number of parametric coefficients terms in the model equation form increases. As shown in the lower left figure, for the complete quadratic polynomial function, shown in blue, that when r squared is 0.9, the cumulative distribution function value for r squared is approximately 0.7, which means for data sets where x and y are actually totally independent of each other, approximately 30% of the time, the r squared value will be greater than 0.9. The steeper the slope or the derivative of the cumulative distribution function as a function of the r squared value, the higher the value of the probability distribution function. So you can see, for example, when n is 5, and the model equation form only has one coefficient to solve for, the slope is quite steep at relatively low r squared values, indicating that the probability distribution function there is high, which means that statistically, this is the most likely region one would get from any random data set. Conversely, one can see that this derivative or slope is quite low in the high r squared value region, for the simplest model equation form shown, which means that by random probabilistic chance, one could still get an r squared value of 1, or very close to it, with 5 observations in this model form, but is less likely than in the lower region. Conversely, one can see that when the model equation form has more coefficients that are solved for, in this case 3, and the number of observations is 4, the cumulative distribution function slope is quite high at high r squared values, so even when y is generated from random Gaussian white noise, just by random probabilistic chance, it appears the r squared value is quite high. The adjusted coefficient of determination, or r squared adjusted, has a formula which includes terms, such as the number of observational data points, the number of parametric coefficients in the model equation form, and whether or not there's an intercept term, to produce an average adjusted r squared value of 0, when the dependent variable is actually independent of the independent variable, and the average value of the dependent variable is consistent with the model equation form. When these conditions are true, the average adjusted r squared value will be 0. However, for any data set, just due to random probabilistic chance, even when there is actual independence between the x and y term, for any data set, the adjusted r squared value can vary dramatically. As an example case, when the model equation form is a complete second-order polynomial, and there are 5 observational values, the probability density function for the adjusted r squared, as a function of the adjusted r squared, shows that there's an equal probability for any individual data set for the adjusted r squared value to be anywhere between -1 and 1. For this example, if we look at this ratio, we can see that n is 5, and p, the number of coefficients solved for, is 3, and the model equation form has an intercept term, and therefore beta intercept is 1. And solving for this ratio, it turns out to be 2. Therefore, if a data is such that the sum of squares residual is 0, meaning that the y values with this model equation form at the 5 data points lies exactly on the input data values of y, then this ratio is 0, and the adjusted r squared value would be also 1. And this is true for any case. When the r squared value is 1, the adjusted r squared value will also be 1. For this example, in the other extreme, if the residual sum of squares equal the total sum of squares, this ratio is 1, which would result in an r squared value of 0, but results in an adjusted r squared value of -1. And for this case, just like all others, it's easy to see that the average adjusted r squared value would be 0. As a result of random probabilistic chance, even when y is actually independent of x, for any individual input data set, the adjusted r squared can vary just like the unadjusted r squared value. However, unlike r squared, the adjusted r squared value has a form which, on average, produces an adjusted r squared value of 0 for all model forms and data point levels when there's actual independence between x and y, and the average value of y is consistent with the model equation form. The figures below illustrate some characteristics of the expected adjusted r squared value when the dependent values are randomly generated as a Gaussian random white noise. The figure in the lower left shows some examples of the cumulative distribution function for adjusted r squared when the number of observations is 4, and these are the model equation forms used. In all cases, the average adjusted r squared value is 0. One can see that when n is not much greater than p, for example, when n is 4 and p is 3, as in the purple curve, the adjusted r squared value can range from -3 to 1. And for the model equation form shown in red, when n is 4 and beta-intercept is 0, the adjusted r-squared value ranges from -1/3 to 1. And for this case, the slope or the derivative of the cumulative distribution function for the red curve is steepest in this region, and therefore when x and y are totally independent of each other, one would expect more adjusted r-squared values in this region. And for the example model equation form shown in purple, when n is not much larger than p, n being 4, p being 3, the steepness of the cumulative distribution function increases as 1 approaches 1, an adjusted r-squared value close to 1 is most likely to be expected. For this model equation form, this number of points, some of the random data sets will result in a very negative adjusted r-squared value to maintain an average adjusted r-squared value of 0. As an example, when the model equation form shown in the blue curve is a complete quadratic polynomial model of order 2 with 4 data points, when y is truly independent of x, when the adjusted r-squared value is 0.8, the cumulative distribution function for adjusted r-squared is approximately 0.75, meaning that approximately 25% of the time, the adjusted r-squared value will be greater than 0.8. There are other metrics used to quantify the goodness of a regression model fit, such as the standard error of the estimate. When the standard error of the estimate is computed not from the entire population, but from a sample of the total population, the standard error of the estimate can be calculated from the following equation, being the square root of the residual sum of squares over the quantity n minus p, where n is the number of data points, and p is the number of independent parameter coefficients in the model equation. One may note that the standard error of the estimate has the same units as the dependent variable.